Have you ever pondered the nature of reality and the limits of our knowledge? What if the more precisely we try to measure something, the less precisely we know something else? In the realm of the very small, where particles dance and intertwine, the laws of classical physics that we've grown comfortable with give way to the strange and counterintuitive world of quantum mechanics. The reality is more complex, more mysterious, and dare I say, more beautiful than we could have ever imagined. One of the cornerstones of this quantum world is a concept that challenges our intuitive understanding of reality: the uncertainty principle. It's a principle that tells us there are inherent limits to what we can know about a particle's properties at the same time. Try to pin down a particle's exact position, and its momentum becomes a blur. Conversely, the more we know about its momentum, the less we can say about where it is. This isn't a limitation of our measurement devices or techniques. No, it isn't a question of building a better microscope or a more precise clock. It's a fundamental aspect of nature itself, woven into the fabric of reality by the threads of quantum mechanics. The uncertainty principle is not just a dry, abstract mathematical concept. It's a profound statement about the nature of the universe. It tells us that the universe, at its most fundamental level, is a place of fuzziness and probabilities, not of certainties and precise outcomes. It's a universe where particles can be in multiple places at once, where they can pop in and out of existence, and where they can be entangled in such a way that the state of one instantly affects the state of another, no matter the distance between them. So brace yourselves. We're about to delve into a world that seems to belong more in the realm of science fiction than science fact. But remember, this isn't some fanciful theory. It's the best description we have of the nature of reality at the quantum level. Welcome to the world of quantum mechanics, where the uncertainty principle reigns supreme. At the heart of the uncertainty principle lies a fascinating concept: the inherent limitation in knowing both a particle's position and momentum with absolute certainty. Imagine for a moment that you're trying to locate a tiny particle. You might think that with the right equipment, you could find its exact position and its exact speed at the same time. Yet, quantum mechanics tells us that this is impossible, no matter how advanced our technology becomes. This is the essence of the uncertainty principle. Now you might ask, why can't we know both? It's a good question. The answer lies in the realm of quantum mechanics, where particles also behave like waves. This wave-like nature means that a particle doesn't have a precise location or a precise speed. Instead, it exists in a blurred state of possibilities, a probability cloud, if you will. This cloud isn't just a representation of our ignorance. It's not that the particle is somewhere in the cloud and we just don't know where. Rather, the particle is the cloud. It is everywhere in the cloud at once until we make a measurement. And here's where the uncertainty principle steps in. When we measure the particle's position, we collapse the cloud to a point. We now know the particle's location, but in doing so, we've spread out its speed. The speed has become uncertain. The same happens if we measure its speed first. We'd spread out its position. The more precisely we know one, the less precisely we know the other. Now, let's delve into the mathematical representation of the uncertainty principle. This principle is typically expressed as an inequality. dx times dp is greater than or equal to h bar divided by 4pi. Here, dx is the uncertainty in position, dp is the uncertainty in momentum, and h bar, or h, is the reduced Planck constant, a fundamental constant of nature. Let's break this down. The greater than or equal to part of the equation emphasizes that we can't pinpoint both position and momentum to absolute precision. The closer we get to knowing one, the less certain we become about the other. Now, what about the terms in the equation? Well, dx and dp represent the uncertainties in the position and momentum of a particle. These aren't your average uncertainties. Instead, they reflect the fuzzy, probabilistic nature of quantum particles. You can think of them as the range within which we might find a particle's position or momentum. And the h-bar, that's the reduced Planck constant. It's a tiny number, about 6.6 times 10 to the -34th joule seconds. This constant is a fundamental part of the quantum realm, showing up in everything from the energy of light particles to the spin of electrons. In the context of the uncertainty principle, it sets the lower limit on the product of the uncertainties. So, the product of dx and dp being greater than or equal to h bar over 4pi means that the more we try to confine a particle's position, the more its momentum becomes uncertain, and vice versa. This equation is more than just numbers and symbols, it represents a fundamental truth about our universe. The uncertainty principle leads us to the concept of wave-particle duality. This duality is a peculiar feature of quantum physics, where particles like electrons or photons exhibit both wave-like and particle-like behavior. This wave-particle duality is intrinsically linked with the uncertainty principle. To illustrate, let's consider a wave. A wave is spread out. It exists in many places at once. Now, if a particle is behaving like a wave, it's also spread out. That's where we encounter the uncertainty in its position. We just can't pin it down to one specific location because its wave-like nature has it spread out. On the other hand, a wave has a well-defined wavelength and frequency, which are related to the particle's momentum. But as soon as we try to localize the particle, to see it as a particle and determine its position more precisely, it's like we're trying to squeeze the wave into a smaller space, and this changes its wavelength and frequency. Hence, the more precisely we know the particle's position, the less precisely we can know its momentum, and vice versa. Now, you might be wondering, why does this matter? What are the implications of this uncertainty principle and wave-particle duality? Well, they're far-reaching and deeply ingrained in the fabric of our universe. They influence the behavior and characteristics of atoms, the building blocks of matter. Think about an atom. Its electrons aren't orbiting the nucleus like planets around the sun, as we might imagine from classical physics. Instead, thanks to wave-particle duality and the uncertainty principle, these electrons exist in a kind of cloud, a probability distribution of where they might be. This cloud, or atomic orbital, is determined by the electron's wave function, and it shapes the structure of the atom and how it bonds with other atoms. And it doesn't stop at atomic structures. The uncertainty principle also plays a crucial role in technologies we use every day. For instance, lasers, those bright beams of light used in everything from barcode scanners to eye surgery, rely on the wave-like behavior of photons. The predictability of their wave-like behavior is what allows us to amplify light in such a precise and powerful way. Semiconductor devices, like those in your computer chips, also owe their existence to the uncertainty principle. The behavior of electrons in these materials, and hence their ability to conduct electricity, can only be explained by quantum mechanics and the inherent uncertainty in the position and momentum of these particles. From atomic structures to lasers, the uncertainty principle leaves its mark everywhere. To bring the uncertainty principle to life, consider a thought experiment with a microscope. Imagine you're trying to measure the position and momentum of an electron using a hypothetical supermicroscope. You're firing light at the electron, then observing the reflected light to determine its position and momentum. The more precise you want to be about the electron's position, the shorter the wavelength of light you need to use. But here's the catch. Shorter wavelength light carries higher energy, according to Planck's equation. When this high-energy light hits the electron, it imparts a kick, changing the electron's momentum. So, the very act of measuring the position with high precision inherently disturbs the momentum. Conversely, if you choose to measure the momentum with high precision, you'll need to use longer wavelength light, which can't precisely locate the electron. This is the uncertainty principle in action, not just as an abstract mathematical concept, but a tangible, albeit hypothetical, scenario. Now, let's take this thought experiment a step further. Suppose we're trying to pin down the electron's position as accurately as possible. The more we confine the electron, the more we localize its wave function, the fuzzier its momentum becomes. This fuzziness in momentum translates to a spread in possible velocity values. A confined electron is, in essence, a restless electron. What happens if we confine it even more, say, to the size of an atomic nucleus? The electron's velocity becomes so uncertain that it can, theoretically, achieve enough energy to escape the atom, a phenomenon known as quantum tunneling. This isn't just theoretical musings, it's the principle behind scanning tunneling microscopes and even the nuclear fusion that powers our sun. So, the uncertainty principle tells us that the more we know about where a particle is, the less we know about how it's moving, and vice versa. As you can see, the uncertainty principle is not just a theory, it's a fundamental aspect of our reality. The uncertainty principle also extends to other pairs of complementary properties like energy and time. This energy-time uncertainty relation, quite like the position-momentum one, asserts that the more precisely one measures the energy of a system, the less precisely one can know how long that energy value will persist, and vice versa. This principle isn't as famous as the position-momentum uncertainty, yet it plays an essential role in explaining natural phenomena like the transient existence of virtual particles. It's these fleeting particles that mediate forces and interactions among the particles we can observe. Now, let's delve into the realm where the uncertainty principle is not merely a theoretical curiosity, but a practical tool: quantum computing. Quantum computers use the principles of quantum mechanics to process information in ways that classical computers cannot. They leverage the uncertainty principle to create qubits, the quantum equivalent of classical bits. Unlike classical bits that can be either 0 or 1, qubits can exist in a superposition of states, being both 0 and 1 simultaneously. This superposition allows quantum computers to perform complex calculations at an unprecedented speed, solving problems that would take classical computers an age of the universe to crack. In addition to quantum computing, the uncertainty principle also finds application in quantum cryptography, specifically in quantum key distribution. This technique uses the principles of quantum mechanics to secure communication, ensuring that any attempt to eavesdrop or intercept the communication would disturb the system, revealing the presence of the third party. The uncertainty about the particle's state in this scenario safeguards the information, making quantum cryptography theoretically unbreakable. These applications are not just limited to computing and cryptography, they permeate various aspects of our daily lives. For instance, the operation of lasers, which are ubiquitous in our modern world from barcode scanners to optical fiber communications, is fundamentally based on the principles of quantum mechanics and the uncertainty principle. Similarly, the functioning of semiconductors, the building blocks of all electronic devices, is deeply rooted in the uncertainty principle. The uncertainty principle, thus, is not just a peculiar trait of the quantum world. It's a principle that has profound implications for our understanding of nature and the development of cutting-edge technology. It's a testament to the fact that sometimes, not knowing everything with absolute certainty can lead to fascinating possibilities and discoveries. In conclusion, the uncertainty principle is not just an abstract concept confined within the walls of quantum mechanics. It has practical implications that stretch far beyond, shaping the world as we know it. It's a cornerstone of quantum physics, an embodiment of the weirdness and wonder that quantum mechanics offers. From the smallest particles to the vastness of the universe, the uncertainty principle continues to shape our understanding of reality.